Benchtop filter in biomedical signal. ECG, EEG and EMG are key diagnostic tools in medical field, but while using this, it is often affected by power line noise which is 50 to 60 Hz. So benchtop filter will remove this noise while preserving the signal. For the design, we must consider signal characteristic, noise frequency, filter roll-off and phase. And then our project goal is to analyze real scenario, design an active benchtop filter and validate it via simulation.
Okay, we talk about problem statement. ECG is a key tool for monitoring heart activity and diagnosing conditions like arrhythmias and myocardial infarction. However, ECG signals are often affected by 50 Hz power line interference, which comes from nearby electrical device. This noise overlaps with the ECG frequency range and can distort important components like the P wave and T wave, making diagnosis difficult or even inaccurate. To solve this, we propose using a second order IIR notch filter, benchtop filter, tuned to 50 Hz. This filter effectively removes the noise while preserving the integrity of the ECG signal. Our project aims to design and implement this filter to enhance signal clarity and improve diagnostic reliability.
From the research paper, we have selected and gathered a lot of information for this project. Our objective is to design a filter that removes 50 Hz power line interference from ECG signals which can affect accurate diagnosis. We choose a second order active bandstop filter with a center frequency of 50 Hz and a bandwidth around 10 Hz. For the filter response, we have selected Butterworth because it provides a flat pass band, preventing distortion of ECG signal. A second order filter is used because it's simple, effective and sufficient to remove the narrow 50 Hz interference without adding unnecessary complexity. To calculate the component values, we use the formula F0 equals to 1 over 2 pi RC, with F0 equals to 50 Hz and C equals to 100 nanofarad. We calculated R to be around 31.8 kilo ohms. We choose the nearest standard values of 33 kilo ohms for the resistor. So the final design we uses resistor 33 kilo ohm, capacitor 100 nanofarads, and operational amplifier is TL072 or LM741. This configuration effectively removes 50 Hz interference while keeping the ECG signal clear.
Next, we are going to talk about the filter design of our active filter circuit. And in multisim, we successfully managed to build this circuit, which is the second order notch filter at the frequency cutoff of 50 Hz. So in this circuit, I'm going to tell you that we are trying to simulate the circuit, and in order to see the clearer results, we are assuming that the resistors are all in the same value, the capacitors are also the same, and the VCC and VEE are at 5.5 volts, and we also are adding a sine wave, which is an AC voltage of peak-to-peak voltage of 1 volt and 50 Hz. So we can adjust the range using the oscilloscope at the top, and we can see the dot plotting or the results of gain and also frequency using the dot plotter below. So this is the overall setup of the circuit. Next, we are going to talk about the simulation results. And first, we are going to see at frequency of 10.589 Hz, which is a low frequency, what is the result that we obtain. So, using the dot plotted as I mentioned earlier, we can see that at frequency of 10.589 Hz, we can see that the gain is close to 0 dB. And this means that it's very little to no attenuation of the gain. So the signals below the frequency or the frequency cutoff are passed through the filter, and it preserves useful low frequency content. As I mentioned earlier, ECG signal components around 0.5 to 40 Hz. This means that below frequency of 50 Hz, it will be passed through the filter.
Next is when F equals to 50 Hz, which is the notch frequency. So from the image, you can see that there is a sharp attenuation observed about or approximately at negative 10.38 dB, and it confirms that effective notch filtering at power line frequency. So most of the 50 Hz interference is suppressed. So the desired behavior for cleaning ECG or similar biomedical signal. So next is that when the frequency is at 709.466 Hz, which is high frequency. So from the image, from the simulation, the output amplitude increased to approximately at positive 17.29 dB. So it indicates that high frequency signals are passed or amplified. And it confirms that the filter targets only a narrow band around 50 Hz. So it is useful for persevering higher frequency components in biomedical signals.
We successfully designed and simulated an active bandstop filter using multisim. The simulation were performed at first one is low frequency, 10.58 Hz. The signal passed with minimal attenuation. The second one is notch frequency, which is 50 Hz. The signal significantly attenuated. And the last one is high frequency, 709.466 Hz. The signal passed as expected.